introduce the speaker of today's talk, Professor Michael Cowling from University of New South Wales, Sydney, and he will give a talk on Brascamp, Lieb inequalities for nonabelian groups. So can hello,
Hello? Okay.
yeah, we can start.
Okay, thank you. So I want to talk about Brascamp Lieb inequalities for non-abelian groups. Now, I understand that a couple of months ago, before the discussion meeting, then you had Jon Bennett talk to you or talk to students. I'm not sure who participated, who did not participate, talking about Brascamp Lieb inequalities. So I think that at least for at least some of you, part of what I say is going to be quite well known, but I apologize in advance for this if you find it tedious, but I hope that in any case you find at least some of it interesting. So it's very nice to be able to give this talk. It would be nicer to, of course, to be in India, but that's a little difficult. So I'm happy to give it online, and I thank Professor Naik for the invitation to do so. And what I want to talk about is partly a survey, what the Brascamp Lieb inequalities, why are we interested in them, and so on. And partly it's an account of work in progress, which is joined with various people, especially Jili and Chongwei Liang, who uh, at least last year were both based in Macquarie University in Sydney, and that's where we did some of our work. So I'm going to first of all discuss the inequalities in quite general terms, and then I'm going to look at some examples. And then I'm going to say that there are some very good reasons. Essentially, when groups are not commutative, it's much harder to have Brascamp-Lieb inequalities. So in the end, I think that there will probably not be all that many interesting Brascamp-Lieb inequalities on non-abelian groups, and so perhaps I'm just saving some of you the trouble of finding this out for yourself. So what are Brascamp-Lieb inequalities? So first of all, let's take locally compact groups G and Gj, where J goes from 1 up to big J. And for each J, we take a homomorphism sigma J that goes from G to Gj. And we also take an index Pj, which is between 1 and infinity. Actually, for some purposes, it's actually reasonable to take Pj, which is not between 1 and infinity, which is maybe between 0 and infinity, but then LP is not a Banach space and there are some complications. So if we take functions fj on gj, then fj composed with sigma j is then a function on G, and then the product of all the fj composed sigma j is a function on G, and the Brascamp-Lieb inequality estimates the integral of this function on G, this product function, in terms of the product of the LP norms of the various factor functions fj. And I suppose it's worth pointing out that if we have fj which are in LP, then we can always just make them positive, and then fj without changing the LP norm, and then fj composed sigma j is also a positive function, and so we don't really need the modulus. And then the point is that at least if this is a positive function, for this integral to be finite, then this product function really has to be integrable in a standard kind of sense. So this is the inequality, and the smallest constant c. C is always a constant in this torque. Sometimes C prime is also a constant, but they're not particularly important as far as this talk is concerned. So let's just call them C and then forget about them. But the smallest C that we can put in here is then called the Brascamp Lieb constant, and it depends on, well, really it depends on the homomorphisms and on the p's that we choose, and implicitly these also include the g's and the gj's and so on. But let's not worry so much about the gj's, but a little bit more about the g. So this is an inequality that can be stated in quite general terms, in terms of locally compact groups, homomorphisms, and so on. Now, let's just have some examples. So first of all, if all the gj's are the same as g, and each sigma j is the identity map, or actually each sigma j could just be an isomorphism, it really wouldn't matter very much, then the Brascamp-Lieb inequality becomes the fact, and now I put the modulus outside, we can do that without any loss of generality, that the integral, the modulus of the integral, is less than or equal to the product of the LP norms. And this is basically Hölder's inequality, and this holds when 1 over P1 plus 1 over P2 plus the sum of all the reciprocals of the 1 over P's is equal to 1. And we can take the constant to be 1. Now, this is a Hölder's inequality is really a fundamental inequality in analysis. It's not so much a question of locally compact groups. It's really a question, it's more something in functional analysis, and in particular, it tells us that if 1 over P plus 1 over Q is equal to 1, then LQ is the dual space of LP. And this is something that is very standard and learned in functional analysis at some point. So if you want to prove this, well, the actual proof of Hölder's inequality is a little bit complicated. It's not immediate, and if we allow ourselves to use interpolation, which is cheating, and I'll explain why it's cheating later on, but if we allow ourselves to take the easy cases where one of the indices is equal to 1 and all the other indices are equal to infinity, then this is just saying that if we take an integrable function and multiply it by a lot of bounded functions, then it's still an integrable function, and we can control the norm of it as an integrable function very easily. And so that's a very easy case. And then if you allow yourself to use interpolation, then you can prove this inequality. Now, in some sense, this is a cheat because, in fact, even to do interpolation, you need Hölder's inequality. So you can't really prove it this way. But it's worth pointing out that interpolation between the easy cases gives a good value for the constant straight away. Now,
so you mean that the cheating means endpoint case? To prove this endpoint case, you need Hölder inequality or what? In the proof of interpolation theory, I didn't get this point actually.
Okay, when you are proving the interpolation, then in some sense, I think you need a little bit. I think you need a little bit more than just the endpoint cases. You need to be able to identify what you get in the intermediate spaces. And yes, interpolation tells you that this is a Banach space, and it will, in the end, it will also tell you that really it is LP, but you have to do a certain amount of work with duality and so on before you really identify the interpolation space with the LP space. It's not immediate. So, but anyway, I claim that as far as this talk is concerned, this is a trivial inequality, because the structure of the mapping sigma j is, it's an isomorphism, but in fact the argument would work perfectly well if the mapping sigma j was just a measure preserving mapping. And so there's nothing special about isomorphism or any group structure. This is a purely measure theoretic fact. So if I'm interested in Brascamp Lieb inequalities in which we have homomorphisms, and we want to worry about properties of homomorphisms, then this is not really all that relevant. But it will be relevant later on anyway. So here's a more interesting inequality. The convolution of two functions on a group is just given by an integral. This is an integral that generalizes the standard integral on a Euclidean space, for instance. And there's Young's inequality for convolution that says that you can estimate the norm of the convolution product of two functions in one Lebesgue space in terms of the norms of the two functions in other Lebesgue spaces, and the condition is that 1 over r is equal to 1 over p plus 1 over q minus 1. And so that's a standard inequality in analysis, and there are multilinear versions of this inequality where instead of just taking two functions, we could take 3 functions or 4 functions or 5 functions or so on. And let's see how that works on the next slide. So if I take a locally compact group, I think I'd like it to be unimodular just to be safe, and let G be a product of 3 copies of this group, and let Gj just be 1 copy of the group, and then I define mappings sigma j from 3 copies of the group to 1 copy of the group. Here's sigma 1, here's sigma 3, here's sigma 2, here's sigma 4. So they're just fairly simple expressions. And now the Brascamp-Lieb product, the product that the Brascamp-Lieb inequality enables us to estimate, it's a matter just of really writing down the definitions, what is each of the sigmas, and then also possibly necessary to change 1 or 2 the orders of integration once or twice if you really want to be careful. But it turns out that this is the same thing as taking the integral over h. This is just any one of the gj's, perhaps g4, but they're all the same, of the convolution of the 3 of the functions calculated at some point, multiplied by the 4th function calculated at that point, and then integrated over the group. Now, the Hölder's inequality is going to say, Hölder's inequality says that LP and LQ are dual spaces. So if this integral turns out to be finite for all F4 in LP of H, then that means that F1 convolution F2 convolution F3 has to be in LP primed of H. So we get an estimate that, well, if there is a Brascamp-Lieb inequality, if the constant is finite, then there's a Brascamp-Lieb inequality. This is shorthand really for saying if there is a Brascamp-Lieb inequality. then the LP prime norm of the convolution is less than the product of the LP1 norm of F1, the LP2 norm of F2, and the LP norm of F3. And this is just the trilinear form of Young's inequality for convolution. So Brascamp-Lieb inequalities encode Young's inequality for convolution. So if we can prove Brascamp-Lieb inequalities, then we can prove Young's in convolution inequality. And actually, in the history of these things, there's sort of perhaps the first serious paper that meant that these inequalities have the name of Brascamp-Lieb inequalities was a study by Brascamp and Lieb, which was a study of the multilinear form of Young's inequality for convolution. So that's really it's really at the sort of at the foundations of these inequalities. And once again, I guess this can be proved by interpolation, where some of these are in L1 and others are in L infinity, then you can prove this inequality and then use interpolation, but it doesn't always give the best constant. And in fact, Lieb was always very interested in finding best constants, and so they found a method to find best constants in this inequality. Now, and a third inequality is the so-called Loomis-Whitney inequality, which is an inequality that arose almost it has a combinatorial proof originally. If we've just got a locally compact group and some index j, which has to be at least 2, and we take G is equal to a product of H copies of J copies of H, and Gj to be a copy of J minus 1 copies of H, then for each J, we can let sigma J going from J copies of H to Gj, J minus 1 copies of H, to be just a homomorphism that forgets one of the coordinates. And then the Loomis-Whitney inequality is that the product of these functions, the integral is less than or equal to, and once again the constant here is 1. It's just the product of the L j minus 1 norms of the functions on the slightly smaller groups. So this is a rather more interesting inequality. If you try to find for what indices pj this is true, whereas often there are conditions like 1 over p1 plus 1 over p2 is equal to something else, here there's only one possible choice of the indices, and so this cannot be proved by interpolation. So it has to be proved by basically an induction on the number of factors and use of Hölder's inequality again. So this is the third inequality that can be expressed as Brascamp-Lieb inequality. And now just a little bit of history. I mentioned already that Brascamp and Lieb, and this was around roughly 1990, considered sort of the generalized multilinear version of Young's inequality. And then Bennett, Carberry, Christenthal considered the case where, well, all of the spaces are Euclidean spaces. So G will take to be Rn, and Gj will take to be R to the Nj. And, well, to avoid some really silly degeneracies, they require that the intersection of the kernels is equal to 0, and that all the homomorphisms are surjective. Now, these homomorphisms are actually vector space homomorphisms. Any mapping from Rn to Rm, which is a homomorphism, is actually a vector space homomorphism. So there's some linearity also as well. And they use linearity quite a lot in their arguments. Anyway, they show that there is a Brascamp-Lieb inequality, that there's a finite constant you can find that is going to make the Brascamp-Lieb inequality hold if and only if, and then they have two conditions. And one is a scaling condition, and it says that the dimension of G has to be the sum of the dimensions of these are the GJs, in fact, divided by PJ. And this is a scaling condition. This is something that says if you dilate all the functions by the same factor, then you also dilate the product by the same factor. And it's very easy to see that when you dilate functions and calculate L1 norms or LP norms, then you change by the dilate to some power, and the power involves the dimension of the space that you're working with. And if there's an LP involved, then you divide by 1 over P. And this gives rise to the scaling condition. And then they get a second condition, which I like to call the Bennett-Carberry-Christau condition, that is a condition that has to hold for all subspaces of Rn. Now, of course, Rn has got infinitely many subspaces, so that in principle there are infinitely many conditions to check. And this is apparently something that has attracted the interest of computer scientists, because they want to work out if you really have to, if something requires checking infinitely many conditions, then it's hard to do it on a computer in a finite amount of time. So they wanted to find ways of doing it in a reasonable amount of time. So anyway, let me just tell you, it's a theorem of Lieb from 1990, which says that on Euclidean spaces, it's enough to look at centered Gaussian inputs. So this means that it's enough to take functions fj, not general functions in LPJ, but just functions that are Gaussian functions and centered, which means that they're based centered at the origin. A centered Gaussian, by a centered Gaussian Rn, I mean a function of the form e to the minus pi, that's just a convenient normalization, and then I take some positive definite matrix A, apply it to y, then take the inner product of y, and this is a typical centered Gaussian. And of course there's still quite a lot of n by n matrices that one would consider. But it's easy to calculate for a centered Gaussian what is this integral, and this also means that it's easy to calculate LP norms and so on. And it means that in the case of Euclidean spaces, the Brascamp-Lieb constant can actually be written down as a finite kind of function. There's a product of determinants. This corresponds to product of LP norms. And then there's one determinant, and this corresponds to the left-hand side of the inequality. And you have to take a supremum over all positive definite linear transformations, AJ, on the groups GJ, which are just R to the NJ. And so this is a slightly complicated expression, but the A's are only finite dimensional, so that makes it a little bit easier to work with. Okay, so why should we generalize this? Why should we look beyond Euclidean spaces? Well, in the context of Euclidean spaces, they turn out to be quite important. They apply in harmonic analysis, partial differential equations, and one of the big problems in harmonic analysis, or there's a group of problems in harmonic analysis, the Kakea problem, the restriction problem, and so on, and it's hoped that they might be relevant to these. There was also a conjecture called the Mizohata-Takeuchi conjecture in partial differential equations. It was hoped that they would help with that. Now, unfortunately, as far as this Japanese conjecture is concerned, a very young student, I think her name is Hana Kairo, in Berkeley just last year actually proved that the Mizohata Takeuchi conjecture is not actually true. So there are sort of replacement conjectures that one has to look at. Now, computer scientists are interested in versions of these inequalities where the linear mappings sigma j are replaced by homomorphisms of finitely generated discrete abelian groups. So these are just products of some power of the integers times a finite group. And it turns out that this discrete version of the Brascamp-Lieb inequality is connected to one of Hilbert's problems. And so that's a reason for looking at these in greater generality. And more recently, Bennett and Jon found the corresponding result when all the groups are products of tori and finite groups. So they were looking at the case of compact abelian groups. And so finally, Jon Bennett and I are finalizing a study for generally locally compact abelian groups. So at least this far we've got, and we have a version of the Brascamp-Lieb inequalities for locally compact abelian groups. So now some of us have begun to think about the non-abelian case. Now, in the abelian case, in the case of Bennett and Tao, they supposed always that the sigma j's were surjective, and the analog of a surjective linear map is a canonical projection of a group onto a group divided by a normal subgroup, a closed normal subgroup, in fact, and that the intersection of all the kernels is just the identity, and that these are equivalent to the conditions that they have. Their arguments to show that you need some kind of non-degeneracy also apply in general. So we're going to look at two examples that unfortunately suggest that the theory is going to be less interesting. So we're going to look at the Heisenberg group Hn and the so-called Ax plus B group, which I'll call Gn. And these are the groups of all real matrices. The Heisenberg group it can be made up of, well, there are different ways of parameterizing it, but I shall just do it by real matrices. And I take 1 x, z, 1 identity, y, 0, 0, 1. These are block matrices. So this is a 1 by 1 block. This is an n by n block. This is a 1 by 1 block. This is an n by 1 block. So this is a row vector. This is over here. This is also a row vector with n entries. And this one has to be a column vector to make this into a nice block matrix. Anyway, these are the elements of the Heisenberg group and of the so-called Ax plus B group. And A really has to be different to 0 because we want to look at invertible matrices. So A has to be different from 0, but it's standard to take A to be positive. So here's the case of the Heisenberg group. There are no non-trivial Brascamp-Lieb inequalities where G is the Heisenberg group. So in other words, if I take G as my source group for all the homomorphisms, and if I take it to be the Heisenberg group, then there are no non-trivial Brascamp-Lieb inequalities. In fact, we'll see that the only possible inequalities are Hölder inequalities, which I said in some sense were trivial because they don't really depend on homomorphisms or any group structure. So if we're going to do this, we need two preliminary results. One is a result in number theory, and it says the following. If you're given a finite number of real numbers and any small epsilon, then you can find a sequence Tm going to infinity so that for all m and for all j, there's an integer so that the Tm is very close simultaneously to an integer multiple of each of the alpha j's. So Tm is close to an integer multiple of alpha 1, it's close to an integer multiple of alpha 2, close to an integer multiple of alpha 3, and so on. This is a very standard theorem in number theory and has been known for 100 years at least. So that's one of our ingredients. The other ingredients is the following lemma. Let me just say that the center of the Hn is a subgroup, and I'll just call it Z for a center. It's the set of all elements G where the X component and the Y component are both equal to 0. So there's only one non-zero entry in it. Anyway, here's a lemma that says if we have a normal subgroup of the Heisenberg group, then either it's contained in the center or it contains the center. But you can't have something that is not contained in the center and contains some non-trivial elements of the center and not others. So this is just a little fact, and it's very easy to prove. So if I take a group, an element in the Heisenberg group, but that's supposed to be in a normal subgroup, then if G is in a normal subgroup, then for any element G prime inverse G prime is also in the normal subgroup. G to the minus 1 is also in the normal subgroup because it's assumed to be a subgroup, and so this product is in the normal subgroup. Now, if you do the calculation, and it's quite easy to do, then there is a bilinear mapping that depends on the X and the Y components of G and the X prime and the Y prime components of G prime, so that this element here is an element of the center where it's possible to identify exactly what it is. Now, if the normal subgroup is not contained in the and this is code for the center, this should have been center. I apologize. If it's not contained in the center, then there's some element in n's whose X component is non-zero or whose Y component is non-zero. And in this case, when you look at the commutator and you let X prime and Y prime vary over n vectors and n vectors, then this bilinear form attains all real values. And so that means that every element of the center appears in this way. And that means that n has to contain the center. And otherwise, n is not contained in the center. So it's really quite easy to say that this lemma is not very difficult. Now let's make this just a little bit more general and say the homogeneous group basically is a nilpotent group. We'll call it Heisenberg-like if it's got a central subgroup Z isomorphic to R with the property that every normal subgroup of G is either contained in Z or contains Z. And the point of this is that actually it's not just Heisenberg groups that are like this. There are other standard groups. If I take the group of upper triangular matrices with ones on the diagonal, then these are also Heisenberg-like groups. So that there are quite a lot of groups like this. And the only Brascamp-Lieb inequality where G is a Heisenberg group is a multilinear Hölder inequality. So how do we go about proving this? So the center, this subgroup Z is isomorphic to R, and I'm going to write every element of this subgroup as being 0t to say there's a whole lot of other elements of the subgroup that have to be 0, and then there's a t in R that this corresponds to t in R. Now, the closed subgroups of Z are all of the form 0 set of integers times alpha for some 0, alpha, and z. That's just standard. The closed subgroups of R are just multiples, are just integers and multiples of integers. Now, let's assume that there is a Brascamp-Lieb inequality, that there is a finite constant, so that a product, the integral of a product is less than or equal to product of LP norms. Well, each of the sigma j's that appears in the Brascamp, each of the homomorphisms that appears in the sigma j is a canonical j projection of G onto G modulo some normal subgroup. The normal subgroup can just be the identity. It can be 0 alpha jz, where alpha j is not equal to 0, or it contains the whole center. It contains the whole subgroup Z. Now, by renumbering, if we need to, we can suppose that the kernel of the homomorphism is just the identity when j is equal to 1 up to I, and then it's not equal to the identity when j is greater than I. So if there aren't any sigma j's where the kernel is not the identity, then I is equal to j. Okay, so if j is less than or equal to I, then this group Gj, which is G divided by the normal subgroup. The normal subgroup is just the identity, so Gj is equal to G. Gj is at least isomorphic to G, so that means that the function Fj is in LPJ of Gj if and only if Fj composed sigma j is an LPJ of G. They're just the same thing, and they might have different Hall measures, so that the LP norms might not be exactly the same, but the LP norm in one place is a multiple of the LP norm in the other place. Now, Hölder's inequality says that if I take 1 over p equals 1 over p1 plus 1 over p2, so on up to 1 over pi, if I sum all of the reciprocals of the 1 over p's, all the reciprocals of the p's for this range where I really know exactly what's going on, then this product has to be in LP of G. We've talked about Hölder's inequality and why this is true. And every function in LP arises in this way. Every function in LP can be written as a product of functions in LP1 times LP2, etc. And we know that this product is integrable, and that means that the P has to be at least 1. So I can apply now the converse of Hölder's inequality, and I can take powers. So the Brascamp-Lieb inequality for the whole group, for all of these, for all j's, is equivalent to saying that since when I take the product when j is less than I get something that's in little LP, then the rest of all of the other products have to be in the conjugate space, which I'll call LP primed. And so I can say that the product for j bigger than I of these LP primed is less than or equal to some other constant, possibly, times the product of the corresponding LP norms. So Hölder's inequality allows me to get rid of all of the homomorphisms which are actually isomorphisms. And this, if I change Fj and replace it by Fj to the P prime power, then this is actually equivalent just to getting an inequality for this product. And now I have to make some changes on this side because I've introduced a P prime power. But what I now have is a Brascamp-Lieb inequality for only some of the homomorphisms, only the homomorphisms where J is bigger than I, only the homomorphisms where the kernel is non-trivial, and I've got a Brascamp Lieb constant, but not for LP, but for a different set of indices, which are these Pj divided by P prime. So if J is equal to 1, then we'd have a multilinear. If J is equal to I, then we'd have a multilinear Hölder inequality. And otherwise, J is greater than I. And otherwise, there are some of these things. And now we're going to derive a contradiction. So there are homomorphisms, all of whom have non-trivial kernels. And that means that for each J that's bigger than I, there is at least some alpha J in R plus, so that the integer multiples of alpha J just in the Z part are contained in the kernel. Now I'm going to take non-empty, relatively compact open sets in G and non-negative functions Fj, so that Fjy is equal to 1 for all y in this is 0 minus epsilon epsilon. So this is just taking a little interval in the center group Z and then multiplying by U. And this should be, I apologize, this should be sigma J of U. But in any case, if this is a relatively compact open set, then sigma J U is another relatively compact open set. So it's easy to take non-negative functions continuous with compact support, so that this is true, and these functions belong to every possible LP space, even if the P is less than 1. Now, Kroneker's theorem tells me that there's an infinite sequence of elements 0 Tm of Z, so Tm's going to infinity as m goes to infinity, and for all m and j, then I can find an integer k, so that Tm primed, which is Tm minus some integer multiple of alpha j, is less than epsilon in size. And by passing to a subsequence, we can suppose that all these sets are disjoint. So now we write down our Brascamp Lieb inequality. This is on the left-hand side. Now, because I'm integrating over all of G, and these sets 0 Tm to the minus 1 U are all disjoint, then the integral of all of G is at least as big. I'm taking positive, or at least non-negative functions here, so there's no problem about this inequality. It's at least as big as this integral. And now I can put this 0 Tm to the minus 1, I can do some changes of variable and put this inside the variable. And so now I just get an integral over U of some function. And the way that things were set up is that this is, well, because all the multiples of alpha m are in the kernel of sigma j, because all the multiples of alpha j are in the kernel of sigma j, then this is exactly the same as taking in the Tm prime. The Tm prime was given by this expression here. It differs by an integer multiple of alpha j. So this is just an identity. And this is equal to 1, and I've got an infinite sum of integrals that have to be positive, even though they're finite. And so this is infinite. And this says that the Brascamp Lieb constant has to be infinite. So that means that we can't have this part where j is bigger than I. So we get back to the case where j is equal to I, and we have a multilinear Hölder inequality. So this is a way in which we can prove that the only possible inequality is a Hölder inequality. Now for the AX plus B group, we can go through a similar kind of argument, and I'm not going to go through all the details, but I will just outline it. So there was sort of several steps. There was Kroneker's theorem. Then there was describing what are the kernels of homomorphisms, and then there was putting everything together. And we have a similar situation here. So we have to know what are the closed normal subgroups of the AX plus B group Gn, and it turns out by a similar kind of argument to the one that we had, that either they're of the form where there are elements A, B, where A is equal to 1 and B is in some vector subspace of Rn, and these are normal subgroups of the affine group. This vector subspace can have any dimension between 0 and n, so there's quite a lot of them. And the other possibility is that then we can get subgroups that take just powers of some number A not equal to 1, and then B, where B is the whole of Rn. Now, the way that we prove this is very similar to the way that we prove the result for the Heisenberg group, and I'm not going to go through the details, but it's a matter of looking at what does conjugation do in the affine group, and it's quite easy to arrive at this result. And now there's a second part, which is actually proving that we cannot have a Brascamp-Lieb inequality, and so without loss of generality, we can say that all of the homomorphisms have to be canonical projections of the affine group onto the affine group modulo one of these normal subgroups, and we renumber them so that the normal subgroup is contained in the part where the normal subgroup has all the A parts equal to 1, and the B parts can be whatever when I is small, and then the nj is at least as big as 1, and anything in Rn when j is big. So we can renumber to make this true. Now, when j is less than or equal to I, G over nj is a group. It's actually another AX plus B group, but we were looking at elements 1b, where B was in Rn, but then when we divide out by some vector subspace of Rn, then effectively we're looking at 1b, where B is in some smaller subspace of Rn, or some quotient space of Rn. So it turns out that it's a group G and J, where naught is less than or equal to nj is less than or equal to n. And on the other hand, when j is bigger than I, then G over nj, I'm looking at a group that consists of all elements A, B, where A is real and positive, and B is anything in Rn, and I'm dividing out by something that has all of the Rn. So all of the Rn is divided out, and then I'm dividing out I'm taking the positive real numbers and I'm dividing out by all the powers of some positive real number that's not equal to 1, and this is a compact group, and that means that I can take Fj to be equal to 1 on this compact group and not worry about it if I want to, and I'll do that for a little while. So let me once again assume that the Brascamp-Lieb constant is finite. In other words, that there is a Brascamp-Lieb inequality that holds. And I will remind you, the group Gn is not a unimodular group. Now that means that it's got a Haar measure that is invariant under left translations, but it's not invariant under right translations. And if you translate on the right by an element AB, then you change the Haar measure by a factor a to the n. That's what the modular function is, and that's just a property of these groups. So I can choose functions. I can take them continuous compact support, for instance, when j is less than or equal to y, and I consider their right translates by a0, then I obtain a homogeneity condition. If I've got a Brascamp-Lieb inequality, then this Brascamp-Lieb inequality has to be valid when I do apply right translates to all of the factors, and when I apply right translates to all of the factors, then I get a right translate of the product function, and a right translate of the product function brings in a power a to the n. And on the other hand, when I look at the right translates and look at the LP norms that are involved, I get a different power which depends on the dimension of the Rn part, and then it's also divided by, because I'm in an Lebesgue space LP, it's also divided by that P. But I'm getting powers on both sides, and I can say that I will only get an inequality if these powers match up on both sides. Otherwise, I could take a to be positive, a to be very close to 0, or a to be very close to infinity, and mess up the inequality. So I get a homogeneity condition, which is this. And I do a second argument by choosing functions that are products of functions on the just on the sort of the R plus part, just on the A part, and other functions on the just the Rn part, and then just translating just the first factor, then I get a similar kind of equation, but because I'm only doing a translate in the first factor, I don't see the nj, I just get a 1, and I get a sum of 1 over pj's, and this has to be less than or equal to 1. So by looking at two examples, I get two inequalities. Now, if I take this inequality, multiply both sides by n, then I will get some j less than or equal to I of n over pj is less than or equal to n. On the other hand, I've got that the sum of nj over pj is equal to n. Now the nj's are less than or equal to n. So if this is equal to n, then the only way that that can happen is if all of the nj's are equal to n. So all of the nj's have to be equal to n for j less than or equal to I. That means if all of the nj's are equal to n, that says that the normal subgroup that I'm factoring out is just the identity. In other words, that all of the sigma j's for j less than or equal to I are just isomorphisms. And this is actually very similar to the case that we had before with the Heisenberg group, where I was able to take the groups I was able to take the mappings that were isomorphisms, use Hölder's inequality, and then say that there must also be a Brascamp-Lieb inequality for the other homomorphisms. And where the powers have changed by some factor, and I'm only looking at some of the homomorphisms. So arguing as in that other case, then I can show that also that this Brascamp-Lieb inequality There must be a Brascamp-Lieb inequality of this form. But this is impossible because for these J's, for the J's that are bigger than I, all of the Fj composed sigma J are constant on cosets of a non-compact subgroup 1Rn, and so their products are also constant on really big cosets, and it means they can't be integrable. So I end up concluding that this means that there can't be any, this part can't be there, and once again, the only inequalities they can have are where the sigma J's are just isomorphisms. And that brings me back to Hölder's inequality. So let me just summarize. We know a lot about Brascamp-Lieb inequalities on locally compact abelian groups. We're now beginning to look at non-abelian groups, and some examples being considered. On the one hand, it might seem that non-commutativity would make things harder, but it also means that there are fewer possible homomorphisms and fewer possible inequalities to consider. So that's the end of what I wanted to say. I just wanted to say that it seems that the non-commutativity makes things makes it harder for there to be a Brascamp-Lieb inequality, so there aren't so many things that you have to prove. And let me just end with a little bit of bibliography. So here are some papers. This is the paper by Bennett, Carberry, Kristen Tao that really proved lots and lots about Brascamp-Lieb inequalities. And as you can see, it's 70 pages long. It's quite a long paper. I mentioned a paper of Bennett and Jon, which dealt with the case of compact groups, compact abelian groups, and that's this. This is a paper that deals with Brascamp-Lieb inequalities for torsion-free discrete abelian groups, and it's in a journal of logical analysis. So this is connected to the Hilbert problem. And this other paper is another paper by computer scientists. These are, at least some of these are computer scientists at Princeton, and they're trying to say that you can actually check whether a Brascamp-Lieb inequality holds or not in finitely meant steps rather than having to check countably many or uncountably many inequalities. Here's the paper by Lieb that says that we can calculate these. And now we've got some submitted papers. So this is a paper by Jon Bennett and myself, which is sorting out what happens for locally compact abelian groups. And here are two other papers. One's about nilpotent groups, and the other is about the AX plus B groups. And so at this point, thank you very much. I've finished, and thank you for your attention.
Thank you very much for a very interesting talk. Are there some questions?
So, are there any result for this semi-simple group or something?
Well, for this, let me say that if you've got a semi-simple group, then there are very few normal subgroups. For semi-simple groups, essentially there are really only finitely many normal subgroups, so that there are very few homomorphisms to consider, and so in some I believe that there's probably some theorem that says that every Brascamp-Lieb type inequality that you could write down for, say, a semi-simple Lie group is some kind of combination of Hölder's inequality and Young's inequality.
Okay.
And that's about all you might be able to find. But that's not yet proved, but that is the hope.
Okay. Okay, thank you.
What about other nilpotent Lie groups, like the H-type group? The argument for the Heisenberg group will go through.
No. This is the thing that for H-type group, typically for an H-type group, the dimension of the center is greater than 1. And for the Heisenberg groups, we really had to use this theorem of Kronecker, which is in the real numbers, and I don't know a suitable analog of Kronecker's theorem in Rn when the center is n-dimensional. So maybe that's just that I don't know enough number theory, or maybe it says actually there are some more interesting Brascamp-Lieb inequalities in this case. It remains to be seen.
But there is a Kronecker's theorem in n-dimensional Kronecker theorem also there. So you cannot use that thing in the.
Well,
yeah.
I'm not sure. I mean, let's say that I haven't been able to work out how to deal with more general nilpotent groups.
Okay.
I should point out that that these papers. So this was put onto the archive in February this year. So this is a very new paper, and we really haven't had time to think through all of the variations on this. But it would certainly. I'm tempted to believe that it's it's probably true that it's just not there aren't all that many interesting inequalities on other nilpotent groups, but it remains to be checked.
Mm-hmm.
Are there any more questions? Looks like there are no more questions. So we would like to thank you very much once again for a nice talk.
Okay, thank you, and it's been a pleasure, and